Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good evening to all our audience, and especially our lecturer, Sir Abdul Rashid Othman. Okay, today we would like to present the assignment of Fourier transform. Okay, the one that will present with me is, my name is Muhammad Amir Razak bin Rahmat, and my other presenter is Muhammad Amir Razak bin Kamal, Muhammad Akram bin Rosli, and also Muhammad Faris Al-Haziq bin Abdul Kamal. Okay, next, we would like to explain what is Fourier transform as an introduction. Also, okay, the Fourier transform has everything. A tool for the application is used in virtually all area of science and engineering. Particularly, it is widely used, especially in terms of discrete Fourier transform, since computational power has increased so dramatically. And in our assignment, especially in electrical engineering, Fourier methods are found in all variables of signal processing, from communication and circuit design to imaging and optics. In mathematical, Fourier transform and the Fourier series are cornerstone of harmonic analysis, and the usage range from number theory to the modern formulation of the theory of partial differential equation. And also, Fourier transform provide a continuous frequency resolution of a function. Example is that the Fourier transform and also fast Fourier transform in signal analysis. A Fourier transform, when applied to a partial differential equation, reduce the number of independent variables by one. The Fourier transform is basically a mathematical function that determines a waveform, which is an element of time into the frequency that make it up. The outcome delivered by Fourier transform is a complex esteem capacity of the frequency. So that the Fourier transform is basically called a generation of the Fourier series itself. This is because both of the terms can apply on the frequency domain representation and also mathematical function use. The Fourier transform convert a non-periodic function f into a transform form where f omega is basically used in widely used, especially in terms of electrical engineering. So that one of the example of the convert a non-periodic function is f omega equal to ft integration of negative infinity to infinity, and then the inverse Fourier transform is basically f power of -1 f omega, which means that it is equal to 1 over 2 pi from infinity, negative infinity to the infinity. Okay, next, in terms of application of electrical engineering, will be presented by Muhammad Faris.
Okay, application in electrical engineering, which is we got application of Fourier transform. In mathematics, a Fourier transform is a mathematical transform which decomposes of function after a function in times or signal into a continuous frequency, such as an expression of a musical code in terms of the value of frequency. So Fourier transform has a many application. In fact, any field of physical science that use sinusoidal signal such as engineering, physics, applied mathematics, and chemistry. So in general, Fourier transform is an apparatus of taking care of physical problem. In this course, the emphasis is on relating the theoretical principle of solving practical engineering. So Fourier transform is very useful in analyzing circuit. While the Fourier transform is a good mathematical tool, its widespread popularity is due to its practical application in virtually every field of science. Fourier transform get involved in many electrical waves, especially non-sinusoid waveform. This is the same way phasor technique is being applied to the circuit with sinusoidal excitation. In operation of electrical circuit, waveform may be effect of manipulated by addition, multiplication, differentiation, integration. A mathematical operation is being applied to solve problem. 3 steps that must be followed to identify the unknown, which is the step is the first convert all element from T domain to the omega domain, and then apply circuit analysis, mesh or nodal to solve the unknown. Convert back omega domain to the T domain, inverse Fourier transform. Next, calculating example in the electrical engineering. This is the example question, which is we're going to use the Fourier transform method to find T. So when the IST equal to 10 sine 2TA, by using the current division, the formula which is H omega equal to IO omega over IS omega, we will get the J omega over 1 plus J omega 3. So if IST equal to 10 sine 2t, then IS omega will equal to J pi 10 delta omega plus 2 minus delta omega minus 2. So the IO omega equal to H omega, IS omega will get the 10 pi omega delta omega minus 2 minus delta omega plus 2 over 1 plus J omega 3. So the inverse transform of the IO omega cannot be found using the table 18.2. So the inverse Fourier transform formula in the equation, we write that IOT equal to F minus 1 IO omega will equal to 1 over 2 pi integrate of negative infinity to infinity 10 pi omega delta omega negative 2 minus delta omega plus 2 over 1 plus j omega 3 time with exponent j omega exponent power of j omega t d omega. So we apply the shifting property to impulse function, namely delta omega minus omega o time with f omega equal with f omega o. Or we can use the integration of integration from negative infinity to infinity delta omega minus omega o time with frequency omega time with d omega. We will get the f omega 0. So to obtain the IOT, IOT equal to 10 pi over 2 pi time with the 2 over 1 plus j6 time with the exponent power of j to t minus negative 2 over 1 minus j6 time with exponent negative j to t, and we will get the final answer, which is 3.288 cos 2t minus 80.55 degree unit of A. So the next application in medical will be presented by Muhammad Akram.
Okay, so I will explain about the application of a medical field. So I will explain about the Fourier transform in a medical field. Okay, for the first one is the nowadays the application of the Fourier transform represent one of the oldest and the most powerful analytical tools in many fields such as applied mathematics, physical science, and engineering. Because of a Fourier transform helps to describe the physical mechanism of collecting and reconstructing data, it also becomes a priceless image processing instrument in other areas which are related to the biomedicine. Okay, so for the example that I want to suggest is Mr. UNIKL has used the Fourier transform for analytical simulation tools that are suited to the parallel magnetic resonance imaging and allow one to build a realistic phantom. This paper introduced analytical simulation tools that are suited to the parallel magnetic resonance imaging and allow one to build realistic phantom. Okay, so including a spline, a contours, Bezier contour, and a polygon. In addition, they take the channel sensitivity into account, for which I investigate two possible models. For the first one is analytical formulation, provide well-defined data in both that spatial and k-space domain. Their main research is to close for the determination for the Fourier transform. Okay, and another example is the Dr. Chimelin. I use a Fourier transform Fourier transform for the mobile stethoscope, which are in signal processing algorithm for pulmonary screening and diagnostic. In the radius, a low stethoscope and smartphone application to record the lung sounds, we discuss problem we encounter with the initial design and demonstrate and improve design that is currently being used in a field. We use the demonstrate an algorithm capable of automatic detection of a wheeze sounds. That automatic wheeze detection algorithm use time frequency analysis and the short time the Fourier transform to identify section of a wheezing and record a lung and sound field. In a medical, Fourier transform involve signal processing, especially in a magnetic resonance imaging, which is an MRI machine. Okay, the Fourier transform in a mathematical technique that allow an MR signal to be decomposed into a sum of a sine wave of different frequencies, phase, and amplitude. Since the special encoding in MR imaging involve frequency and phase in natural and manageable to analysis by Fourier technique. Understanding MRI technique require a basic understanding of the Fourier transform accomplished MR imaging encoding feeling of a key space and a wide spectrum of artifact and all rooted in a Fourier transform. Okay, so this one is the picture of the MRI and is the second scanner diagram. With the respect to the MRI, the model sign we wish to right is the MR, the revelation containing the recurrence and stage encoded spatial data important to develop a picture. Following the cut choice angle for average to turn revelation grouping, which include a specific imaging plane, all turn frameworks process are the similar recursion and stage as directed by the fundamental attractive field. Now, all the protons in ideal imaging plane appear to the identical to the Fourier change. The alteration of the supremmost powerful changing angle field present, especially subunit varieties in a recurrent and stage over the local of integer ROI. Adequately recording the large system for all external spatial frequencies. The numerous pinnacle amplitude in the MR specifically range speak to the overall commitment of a specific biological metabolics in a given area in integral each constructing somewhat in a revelation recurrence because of the remarkable compound structure. Okay, so the next one, Mr. Izzat will explain about the calculation of example in medical field.
All right. As we choose the medical field as our assignment, so it has its own calculations. So for the discrete Fourier transform technique, is used to calculate the frequency content of the simple signal. The signal can be from any source with a prediction of suspected political behavior. It can also be used to analyze a non-predict signal. The one-dimension discrete Fourier transform of the signal xn is a sequence defined over the interval from 0 and -1 is given by. So as you can see, the xk is given the formula, which is sum of n1, which is the number started from 0, where k are the variables from 0, 1, 2, and etc. until it's 1, -1. The corresponding inverse the discrete Fourier transform of the sequence xk given a sequence xn defined on the interval which is 0 as n-1. So as you can see, the xk is included into the formula, which is it will produce also xn, which is the formula is 1 over n sum of n -1, which is a k equal to 0, xk exponent the power of j 2 pi k over n. Applying this an imaginary I, which is the variable x and y of the size m times by n given, which is sk, kx, and also ky, which is s, we produce the coordinates for this. And for the two dimensions 2D, discrete Fourier transform is given by I, x, and also y equal to 1 over mn, sum of m minus 1 and sum of n minus 1. So the x will start from 0 and also the y start from the 0. So the function is s, k, x, and ky times by exponent exponent the power j 2 pi times by kx over n over m and plus ky y over n, where the variable kx and ky are frequency variable and xy are spatial variable. The Fourier spectrum, which is s, kx, and ky, phase angle, we produce kx and ky, and the power spectrum p, kx, and ky is given as shown the formula. So, and we go to the where r, kx and ky and I, kx, ky are the real and imaginary part of s, kx, and ky respectively. One of the important property of discrete Fourier transform is repairability. The standard 2D dimension of discrete Fourier transform equation can be expressed in separable from one dimension from as the formula given as in this figure. So where the rectilinear scan are not immune to artifacts, but such artifacts are well controlled and easily identifiable. So we go to the discussions from this medical field. The Fourier transform is integral to all modern imaging and it's particularly important in MRI. The signal received at the detector receiver coil in MRI, piezo disc in ultrasonic, and detector array in CT scanner. It is a complex predict signal made of a large number of consequence frequency, example bandwidth. This can be visualized as a multiple sines and or cosine with a long time axis. The Fourier transform represents the same data over a frequency axis. A common example is MR spectroscopy image in which different molecules are at a different frequency along the axis. The Fourier transform is a fundamental mathematical tool in the decomposition of the completed signal, allowing the students to see the clear and understand more about the frequency and amplitude component hidden within. In the process of the generating an MR image, the Fourier transform resolve the frequency and a phase encoded MR signal that compose K space. The 2D inverse Fourier transform of a K space is a MR image we see. It's widely used in the signal analysis of the basic thresholds in radiology and integral to a modern MR image formation, also particularly important in MRI. The signal received at the detector, which is a receive coil in MRI. Piezo disc in ultrasound and detector array in CT. This is a complex predict signal made of the largest number of consequence frequencies, such as bandwidth. This can be visualized as multiple signs of the or cosine wave along a time axis. The Fourier transform also represents same data over the frequency axis. Understanding MRI technology require a basic understanding of the Fourier transform accomplished. MR image encoding a feeling of a K space and wide spectrum of artificial all rooted in the Fourier transform. And we go to the conclusion, which will be concluded by Amirul.
Okay, so as the conclusion, I will conclude basically what what actually we are doing in this assignment from the start until conclusion. Basically, Fourier transform is named in the honor of Joseph Fourier, one of the greatest name in the history of mathematics and physics. Mathematically speaking, the Fourier transform is a linear operator that maps a functional space to another function space and decomposes a function into another function of its frequency component. The formula used to define Fourier transform vary according to different authors. We have like 3 authors, but they are essentially the same, but using different scales. From this assignment, we can learn more details and deeply about the Fourier transform, which is an essential component of modern applied mathematics. It forms an exceptionally powerful analytical tool for solving a broad range of partial differential equations. Fourier transform has tremendous use in many branches of applied science, physics, and electrical power engineering, and also basically medical engineering that being mentioned earlier. In medical field as well, Fourier transform is very important in order to analyze the result. Fourier has its own specific calculation method to get the result even in medical field, such as MRI, which being mentioned in this assignment, while the number of basic functions are more flexible and thus the computation is more efficient based on the method. Using the magnitude of Fourier transform, one may represent the functional signal as multivariate signal and thus able to apply a linear classification method. And our method itself is already a fast and efficient way to reconstruct signal or images, while all those have been tested truly in more rigorous way in future research. Thus, the Fourier transform is also called a generation of the Fourier series. This term can be applied to the both frequency domain represent and the mathematical function used. The Fourier transform helps in extending the Fourier series in non-predical function, which allow viewing any function as a sum of a simple sinusoidal. Therefore, what we can conclude that basically all of the above, all being mentioned earlier is basically how we want to apply the Fourier transform in terms of electrical engineering and also medical engineering. So this is basically all the 9 references that being used in our finding and calculation for our assignment. Therefore, it concludes our presentation regarding the assignment of Fourier transform today. Thank you, everyone.